Do you know you can make AI models smarter and faster without retraining them? Hi, I am Jain, an aspiring AI engineer. Check out my portfolio, link will be in the description box. Today, we are diving into the AI revolution from the generative AI basics to advanced concepts like LoRA. This video is perfect for beginners and I will break down the complex concepts step by step with examples and analogies. You might ask, okay, Jain, there are so many other creators out there who are more experienced than you, covering the same topics. Why we have to trust your content? Okay, hear me out. Before uploading this video, I watched most of them. They were lacking the clarity, especially if you are curious. I promise 80% of this content of the video is based on the research papers. I will show you at the end of the video. I am very excited to guide you in this AI journey. Let's get started. Yes, let's understand what is generative AI. Generative AI is type of artificial intelligence that creates new content based on what it has learned from the internet or the existing content. I hope you understood. Now let's understand how to consider and differentiate between a predictive ML model and Gen AI model. Let's y is equals to f of x. Y is our model output and f is our model and x is the input data. If our output of the model is in natural language, like when we ask the chat GPT to use something, to ask if you have any doubt, you will ask, it will respond in a human English language, right, which is in natural language. Now when you go to Dali, if you will ask to generate an image, it will generate an image based on the numerous images it has learned that are present on the internet. In a similar way, if the model able to generate audio and video, we will consider the model as a generative AI model. If you want an in-depth explanation, go and watch video from Google Cloud Tech channel. I will give the link in the video description. Now let's understand what is fine tuning. Fine tuning is nothing but making small adjustments to the foundation model so that it will be expert. It will do its best in the downstream tasks or a specific field. Now let's understand the keywords here. The foundation model. Foundation model is nothing but it is a large AI model that is trained on broad data so that it can be applied across a wide range of use cases. For example, if you take the example of ChatGPT, underlying GPT model is GPT 4.0. Now they are giving for a limited time. Now that model we are using for wide range of tasks for content creation, like generating posts, video scripts, blogs, and asking for decisions, asking for suggestions, asking for ideas, and for medicine different use cases we are using that because it is trained on broad data that's present on the internet. Okay, now we understood foundation model, Jain. Now what is downstream task? Those are the tasks where we want our model to be expert in. I have written some of them here. You can see image classification, text classification, and so on and so forth. Now let's understand what is full fine tuning. Now we want our model to be expert, let us suppose, in image classification. Now you have prepared the data set. Now you will retrain all the model parameters. If you retrain all the model parameters with this data set of the image classification, then that is known as full fine tuning, means updating all the weights. That is nothing but full fine tuning. Now we are having some other techniques. Parameter efficient fine tuning techniques are there. What are parameter efficient fine tuning? Let us see. See, in the name itself, fine tuning means we understood is the basic adjustments we have to do. Some adjustments. Now parameters are nothing but the weights and biases. Now how we can efficiently use the parameters, the weights and biases, so that we can fine tune. Let's understand. Before understanding PEFT, let's understand what is its need. We understood what is the need of fine tuning to make the model expert in a specific field. Now what is the use of parameter efficient fine tuning means? Every day we inject data to the internet. Now the data is growing. Now you can see GPT-3 model, GPT-3o, GPT-3 is trained up to 2023 November, GPT-4o trained up to June 2024, like that. Why they have mentioned? Because new data is injected every time. We have to retrain the complete model. We have to do the full fine tuning every time, where we have to include all the resources that were used earlier when we are preparing the model, like the GPUs, electricity, cost, time, everything is same, right? Because you're doing full fine tuning. You are efficiently not using the weights, and you also have to do the deployment each time, every time 175 billion. How much cost effective it is. So it's very critical challenge for deployment. For these concerns, we introduced parameter efficient fine tuning techniques so that we will efficiently fine tune the model. One of them is low rank adaptation, LoRA. Now, before understanding LoRA, let's understand, are the existing solutions good enough to solve this? The existing techniques like adding adapter layers. See guys, imagine a architecture. Let us take, I have this architecture here written. Now, in this architecture, I will insert two more layers. Those are adapter layers. Adaptation is nothing but making expert in some specific task. We add two more layers at the end or evening. There are different types, there are different techniques in adapter layers as well. We are not exploring because it is out of scope. Our main aim is to learn LoRA. Why we need LoRA? Means we are just understanding, because these have some consequence. See, when we have two more layers here, what will happen? We are introducing some latency, right? Now let us suppose here are 1000 weights. After adding two layers, we will be having 1500 weights now. Now when we give an input, it will take more time to give the output, right? Because we have to do more calculations than before, since we added two or more layers now. That is the problem with adapter layers. I hope you understood. The problem with adapter layers is it will introduce the inference latency, which original model don't have. Original model latency is X. Means now after using adapter layer technique, we will be having X plus something inference. Now we have this, but we want real time. We want always the model to be very quick. This is the consequence that we have with the adapter layers. Now there is another technique known that directly optimizing the prompt. See, it is also very hard to optimize the prompt. Let us suppose there are two prompts here. Generate a smartphone product description. This is prompt. And prompt prefix fine tuning. Prefix tuning is nothing but adding some prefix before the prompt, like positive tone. View the output in the positive tone. We are already giving this information how we want at the start itself. Means we have to add this prefix to every data point of our data set. That is one critical point. Then another critical point the researchers notice across different various tasks is that using prefix tuning, performance of the model changes non-monotonically. It is not increasing when across different tasks. It's very difficult to optimize as well, and it is very hard to prompt as well to do the prefix tuning. These are the two consequences that we have with the existing techniques. I hope you understood the pain why we need LoRA. Now let's get into our method LoRA. Low rank adaptation. Low rank. What is rank? Rank is nothing but the number of independent rows or columns in a matrix. Now what is independent rows and columns? Please explore the videos on YouTube and come to this video to understand what is rank. Now what is adaptation? In the context of large language models, adaptation is nothing but adapting, means becoming an expert in some specific field, let us suppose. Now I hope you also know, if you know the backpropagation or weights and biases of artificial neural network, we can also write the weights in a weight matrix. I hope you know this. I just want to recall this. Now the authors are saying that when we are trying to adapt to a specific task, they came to know that they are telling, hey Jane, we came to know that pre-trained language models have low rank, low intrinsic dimension. Okay, let's explore what is intrinsic dimension. I will not read this definition, bookish definition. I will show you. It is present in the research paper itself, but I will explain you through the example. Let's imagine theta d consists of all the 175 billion parameters of GPT-3. Now the authors are saying, during optimization, we don't need all of these 175 parameters. We only need some of them. How to find that some of them is a different approach, by linear projection. Different projections are there to get that, but we are not concerned with that. What they are telling is that for optimizing during fine tuning, we don't need all these 175 billion parameters weights. We only need some of them, a smaller subspace of them. If this is a space, consider this as a space, and a smaller subspace considered as theta small d, only 1 million of them. And we all know that there will be so many subspaces for this space, 175 billion. But which one to consider, Jayant? If you ask me, then authors are saying that we have to consider that theta small d, which gives 90% accuracy of the full fine tuning with all the 175 billion parameters. I have written here. We have to select the theta d such that it gives 90% accuracy of full fine tuning. I hope you understood. Now we call that theta d as intrinsic dimension. I hope you understood what is intrinsic dimension. Now the takeaway from this, the intrinsic dimension concept is that for large language models, we understood that there exists a smaller subspace of parameters or nothing but weights to optimize to get the 90% accuracy. We don't need to optimize all the 175 billion parameters weight that we got from this. Now the authors inspired, the LoRa authors inspired from this and said that for the large language models there would be intrinsic rank as well for large language models. Okay, first let's understand what is intrinsic rank, then we will connect the dot between the intrinsic dimension and intrinsic rank. Okay, so now please see me. Imagine an architecture here of GPT-3. Okay, this is the architecture of GPT-3. Now let's focus on the first layer, only the first layer. Okay, it has 1 million parameters. Since it has 1.175 billion, only consider the first layer has 1 million weights. I also showed how the weight matrix will look like. This is the weight matrix. I took in my hand. Here is the weight matrix of the foundation model. Okay, and it is very heavy. I cannot hold it. My hand is shaking. Okay, don't worry, Jane. I am there with you. The LoRa says. Okay, LoRa, how can you help me? Okay, it says me that please freeze this W in your another hand. Okay, I will take this into my another hand and I will freeze it. Okay, what I have to do next? It says consider two matrices A and B. Okay, LoRa A and LoRa B. LoRa A here and LoRa B here. Two matrices are there in my hand. I hope you can see here. And the LoRa A is a Gaussian initialization and LoRa B is 0. Others I see why you are initializing like this. I asked LoRa. It says, please, we are experimented with so many different formats, but we observe that it is giving the best result. And at the start, since B is 0, LoRa B is 0, if you multiply LoRa B into LoRa A, it will be 0, right? Okay, LoRa, I understood. Okay, now you pre-train this LoRa A and LoRa B instead of this W during the fine tuning. Okay, let us consider, guys, image classification is our downstream task, and A and B our matrices. LoRa A and LoRa B we considered, and we are pre-training them instead of this W for the image classification. Now, okay, these are pre-trained now. Okay, these are pre-trained. Now what I have to do, LoRa? Now you just multiply them. Okay, I multiplied both of them. LoRa A, which is, let us consider 1 million, right? LoRa A dimension is 1 cross 1000 and LoRa B the dimension is 1000 cross 1. Now if I multiply LoRa B into LoRa A, I get 1000 cross 1000, where the dimension of the number of parameters of W also same 1 million, and its dimension is also 1000 cross 1000, right? We freeze it. It is in my hand. Now you see, it says to multiply LoRa B. Okay, LoRa B into LoRa A multiplied. Now I got delta W, another matrix of this fresh trained rank decomposable matrix. From this fresh trained rank decomposable matrices, I got A and B. I multiplied them, I got delta W, and here is W, which is already present. Okay, this is LoRa layer weights. These are foundation model weights for a particular layer. Okay, and my question is X. I hope your question might be Y. Now I am multiplying this delta W into X. I get some output, LoRa output, and this W into X. I get foundation model weight output. Okay, I have both of them. And the LoRa authors are also saying that if you want to control the output of LoRa on the foundation model, we are introducing some normalization for you so that you can control. Okay, what is that normalization, LoRa authors? They are saying that alpha by R. Okay, we can multiply with alpha by R, where alpha is the learning hyperparameter and R is the rank. Alpha by R. Okay, I multiplied with them. We kept rank as 1, right? See, guys, LoRa A dimension is 1 cross 1000. LoRa B dimension is 1000 cross 1. Please listen my words very carefully. We are multiplying LoRa B into LoRa A, not LoRa A into LoRa B. LoRa B into LoRa A. Now 1000 cross 1 is the rank here. Low independent rows, number of independent rows here. Authors are saying large language models will have low rank. That's why I keeping 1 as a rank here. In general, we will keep 4 and see 1. I hope you understood. Now alpha by R, we scaled it. Now we got the output of the LoRa. We have that. We have this. We just have to add, guys. That's it. We fine tune the data set. We fine tune our foundation model of layer 1 for our image classification data set, of our image classification task. In a similar way, we take the second layer, delta W, we freeze it. A and B matrices will be there in such a way that if I multiply B into A, I get the same dimension as W. Now I will get delta W. I will retrain delta W Scaling, if you want, just chat. Layer 2 is also fine tuned. Layer 3, layer 4, similarly all layers will be fine tuned at a time. That's it. That's how LoRa works. I hope you understood LoRa now. That's it, guys. We understood LoRa. Now I will show you what I have written here. Now see, W naught is the weight matrix of the layer, and delta W is B into A, and B is initial. See why B is zeros and A is Gaussian, because they experimented and they came to know this is the right. In this way, we are getting good result. It is all about experimentation. I hope I am clear. Now, I have already told we will freeze this W naught. We only train A and B matrices of that layer, and we multiply with that layer. And I also told we apply LoRa to the layer, not the foundation model. Foundation model, in so many ways you see fine tuning will be done on a model. It's right. We will do on a model, but in model there are layers. We do fine tuning layer wise. LoRa is applied to each layer. I want to clear about that. Now we will also scale. I already told you why we are scaling, because we want to control the effect of LoRa on our foundation model. You can read it, guys. I will give the complete notes video in the description of this video in my portfolio. And let's take on another example. Here see Eminis dataset is there. I hope you know. If you are in the AI field, see output there will be 10 classes 0 to 9. Input is 1 x1 to x784. In the first layer there are 1000 neurons. In the second layer there are 2000 neurons. Output 10 neurons will be there. Layer 1, layer 2, layer 3. In layer 1 we have 784 input, 1000 output. 1000 biases will be there. For each neuron one bias will be there. See, layer 2, these many weights biases, these many weights biases. I hope you understood, guys. W naught, how I created W naught. Now let's apply LoRa to the layer 1. Layer 1, see, layer 1 we have W naught and B naught, and the LoRa A, LoRa B will be there, right? I'm taking LoRa and LoRa B, and if I multiply LoRa B into LoRa A, we get W naught. See, guys, 1000 cross 1 into 1 cross. We have to create the LoRa A and LoRa B such that multiplication should give the same size as W naught. Now LoRa B into LoRa A, we get delta W. Now you can say me, Jane, instead of 1 you can also keep 2 also, right? 3 also, right? 4 also. Yes, we can keep, but we have to understood that their researchers are saying that, the authors are saying that low rank is good for large language model. They understood that. They are telling for us we can also increase that. We can also increase the rank as well. Here 1 is nothing but the rank here. I hope you understood, guys. Number of independent rows that present in the independent rows or columns in a matrix. For when we are pre-training, when we are fine-tuning for image classification dataset, let us suppose what we do in the layer 1. Now the updated architecture contains W naught, B naught, and this LoRa A, LoRa B. And for layer 2 as well, LoRa A, LoRa B will be there. For layer 3 also, LoRa A, LoRa B is there. This is your task. This is your homework. If you are able to write LoRa A, LoRa B, then you have understood. Please comment down in the comment section whether you understood or not, whether you done the homework or not. And small homework, guys. Now see, we freeze W naught and B naught, and we train only LoRa A and LoRa B for the layer 1. For the layer 2, LoRa A and LoRa B. For layer 3, LoRa A and LoRa B only we will train. We don't train these. Now after training, I already told delta W we get. If you want, we scale, and then we add to the W naught into X. I showed you here. See, this is our output. How we get output. I hope you understood LoRa, guys. I hope you understood. Let's calculate the parameters. I hope you know how to calculate the parameters. I am not counting here. The total number of parameters for the architecture I have mentioned above are 2.8 million, and the parameters with LoRa 2.83, and the only LoRa parameters are 6794, guys. How crazy is this, guys? I hope you understood. See, we have to train 2.8 million for full fine tuning to be expert in a particular field, but now we are only training 6794 for the downstream task. I hope you understood the significance of LoRa. If you have any doubts, please comment them. I will love to reply to you back. If you loved this video, please share, subscribe. That's it. I will see you in the next video. Thanks for watching.